All right, welcome everyone to this session. My name is Chao Wang, and I'm going to be co-presenting this session with my colleague, Viktor Rozgic. He's sitting right there. And we're both part of the Alexa team working on developing machine learning algorithms for speech and audio processing. So in the next 50 minutes or so, we'll be talking about recognizing emotion from speech by computers. If you're new to speech emotion recognition, we hope that you'll gain a foundational understanding of this exciting field after our session. And if you are a practitioner of machine learning yourself, I hope that you'll find the topic of speech emotion recognition interesting, and maybe you even have new ideas for us to try. For students in the audience, we're always hiring. We have lots of intern and full-time positions. So if you're interested, please look us up after the session or just take down our emails at the end of the presentation. So I'll get this started with an overview of speech emotion recognition. I'll talk about how you represent emotion, how do you get emotional data for training, and how do you train the emotion recognition models to achieve high accuracy. A lot of the materials I will cover are actually drawn from studies published in the literature for the past 20, 30 years. My hope is to convey to you what are some of the common understandings and practices that are shared by researchers in this field. My colleague Viktor will actually take over and talk about two papers that we recently published on this topic. He'll discuss some of the neural network architectures and experiments that we explored aimed at achieving high accuracy for this task. So let's start with the why. Why is emotional awareness by machines desirable? This morning, Dr. Kate Darling gave a very interesting keynote speech about humans expressing emotions to robots, even when we know perfectly well that robots do not, or robots, or they're just basically machines or devices that they have no feelings, right? And I want to even go ask further a related question, like how many of us or how many of you have maybe thanked your virtual assistant for being helpful or swore at your computer because it was really dumb? So looking at the other angle, humans express emotions to computers all the time. For people work on building human-computer interaction technologies, this seems like a great opportunity to basically make the customer experience better, right, by understanding human emotions. So you say, okay, that makes sense. If I know the user's emotion, I can adjust. And that is true. So in a lot of the, say, computer-aided learning systems, you can pay attention to the learner's emotional state, and you can adjust, say, the presentation of the material or the pace of the learning to achieve the best effect for that student. But even when you just have tools that can allow, say, computers can understand emotion, they can be used to provide tools to humans to make them more effective. So for example, if you have machines or computer algorithms that can analyze user reaction, either from video signals or others, then you can use that in sort of like large-scale usability studies. So for example, in gaming industry, you can look at sort of the gamer's reaction to see, okay, there's a frustration point in a particular game design that we need to iterate or improve on. Or in marketing, which is not my favorite use case, but you can use emotion recognition to gauge the viewer's reaction to, say, marketing materials, a commercial or something else, and then you can fine-tune your material to achieve the desired effect. So and actually, computers, computer awareness of emotion can even help enhance emotion awareness by humans. So we probably all have experienced road rage, right? You're driving and there's just like traffic or some really annoying car just keeps on blocking you. So researchers in Switzerland are actually teaming up with automotive company to develop and test sort of road rage or fatigue detectors. So they mount cameras behind the steering wheels and observe the driver. And once they detect either fatigue or road rage, they can gently point that out to the driver, for example, to make the driving experience safer. So in all these applications, you need to basically first build the capability of being able to perceive human emotion state. So speech emotion recognition has been an active research area for many, many years. I don't know, 20, 30, or maybe even longer. There's several leading institutions in this area. So I named a few here: USC, University of Southern California, SAIL Lab, and certainly MIT Media Lab is the forerunner for affective computing area. And also this GLAM, which is Group for Language, Audio, and Music at Imperial College of London. They all have published numerous papers pushing forward the state of the art. Emotion representation theory is the foundation for emotion recognition research. It provided a methodology to describe emotion so that we can label the data with the appropriate target so that the machines can learn to predict. Advancement in signal processing and classical ML, classical machine learning, improved our understanding of the emotion, of what the signal level information in speech is the most useful for recognizing emotion. So in that period of the research, a lot of scientists focused on finding what is the best feature that is representing emotion. And they use that feature with, say, classical classifiers like support vector machines to achieve the best results. And as a side effect, we actually understand, okay, these are the features that is most effective at classifying emotion. In the recent years, with the success of deep learning in areas like computer vision or speech recognition, emotion recognition also pivoted into this new deep learning technology-based approach. So instead of doing feature engineering, you're using neural networks basically to do both the feature extraction and the inference model optimization. You learn all these from data. And this is also fueled by the abundance of digital audio data from a lot of the multimedia sources. So you can basically label these data through large-scale crowdsourcing. And also, even if you can't label a lot of data, you can use semi-supervised or unsupervised learning technologies to utilize the data that's unlabeled. Sorry. So what are some of the key components to emotion recognition by computers? Before we answer that question, let's first take a look at how humans perceive emotion. Certainly people don't just perceive emotion from speech, right? We pay attention to a lot more information, like the facial expression, the body language, but we are able to perceive emotion from speech only. And let's just go through an exercise together. I selected some audio from this USC AlMoCab database. This is a database, emotion speech database that is available for speech, for research purposes. So I'll play each audio, and then you, the audience, please think about the emotion you perceive from listening to the audio, and then see if your perception matches the labels that is chosen by the annotators of this database. All right, let's start.
What do you want me to do? What do you want? Yeah, I know. Wow, I'm shaking. I can't even.
Yeah, we're pretty close.
Okay, well I'm gonna go ahead and check on that for you. You're coming from, where are you coming from?
All right, that seemed pretty straightforward, right? Well, emotion perception from speech is not always that simple. This is because in a lot of the cases, you actually rely on context, the longer conversation, for example, in order to get a better sense. So I'm going to play you another example. In this case, I'll first play a single utterance from a conversation. Let's simplify the task. You don't have to tell me the emotion. You just have to think, is it positive, negative, or neutral? And then we'll continue.
Yes, exactly.
All right, so it's pretty short, and you can say it's pretty maybe neutral. I don't know, it's hard to tell. So let me play you the conversation.
You do the direct. It is taken right out of your bank account.
Yes,
correct?
exactly.
Yeah, so that did go through.
Are you taking the late fee off of my account then?
I can try to do that for you, certainly.
Because I paid it on time.
All right, so you kind of know that the conversation is two people kind of arguing.
Yes, exactly.
So does this example now sound a little more like negative to you after listening to the whole conversation? All right, so let's talk about the first element of emotion recognition, which is representation. So it's very natural to represent emotion using categories, right? So I listed actually 7 here, but it's supposed to be this big 6: anger, disgust, fear, happiness, sadness, and surprise. But of course, there's neutral, which means there's no emotion expressed. A lot of the times, it's actually really challenging to decide the number of categories that's suitable, because certainly human emotion is more than this, right? You can have contempt, you can have excitement. So how do you decide what is the right number of categories? And you're kind of torn between, okay, you need to have it fine-grained enough so that you can represent all the emotion close enough, right, in the data that you're dealing with. But if you have too many, then the annotators might have difficulty to say, sometimes even for anger and disgust. Like, they're so close to each other that it's very difficult to distinguish them apart. So how to choose a good inventory of the categories is really hard. So in recent years, this dimensional representation is gaining popularity for machine learning research, or for building machine learning systems. According to this representation, emotion can be described by numerical values along 3 dimensions: valence, which is talking about the positivity of the emotion; activation, which is the energy of the emotion; and then the dominance, which is the controlling impact of the emotion. So you have valence, negative, and positive. So a -2, for example, indicates a very negative emotion, such as anger or sadness. And a +2 indicates a very positive emotion, say happiness. And for activation, sadness usually is associated with very low activation, but happiness, anger would be associated with, but be perceived as having high energy in activation space. And thinking about dominance, so you have say anger and fear, they're both negative feelings, but anger is positive in dominance, but fear is a submissive type of emotion. So now let's look at how do we get data to train the emotion recognition system. The best data is usually, real data. Real data meaning naturally occurring data. However, for emotion, natural occurring data also is predominantly neutral, right? People don't express strong emotions all the time. So when you build a machine learning system to predict emotion, you want it to work well in all the different spaces in the emotion space. So you do need data that represents the entire emotion expression space. So how do you get data that is emotionally rich? There are two typical strategies. One is try to mine data from existing large quantities of multimedia data. For example, podcasts or radio, TV programs, movies. And then you can mine the data to achieve the desired distribution or coverage of different emotion content. So there's a data set also publicly available for research purpose. It's called MSP Podcasts. It is done exactly by that approach. So the data was selected from podcasts, audio recordings from podcasts, and then the data was labeled through crowdsourcing, and then it was carefully selected so that it's covering the entire activation valence space. Another method is actually to get people to act, to get the data. And this requires careful design of your data collection protocols. And you also better hire people who are good at acting, because otherwise, the signal will be very, very controversial. So the IO mocap data developed by USC was actually collected that way. So the audio samples you heard earlier was actually from conversations of two people acting out scenarios. So now let's look at some data in this emotion dimensional space. So this figure showed the distribution of, let me see the place, yeah. Activation is this way, valence is this way, and dominance is that way. So this is, say, all the utterances that are labeled as angry by the annotator. So if you focus on this plane, which is activation valence, you'll see that anger is largely in this negative space for valence and positive space for activation. And dominance-wise, it's also positive. So disgust is actually fairly similar to anger in that space. And that's not surprising, right? It's a very similar emotion between these two. So this is sadness. And let's just take a quick look here. Activation-wise, it's shifted towards the negative territory here. Valence is also negative. And dominance is also negative. And happiness is the opposite on the valence side. So you see that it's positive valence, high activation, and sort of neutral from a dominance perspective. And you also have neutral data, which is around sort of neutral in all the different dimensions. And if you look at all the data plotted together, you'll see that there are some differences between the different classes, right? Other than, say, anger and disgust, which are very close together, the other classes are relatively separate from each other. However, there's also significant overlap. And this is because emotion expression is very complex. And emotion perception, say by the annotators, is also very, very based on judgment, right? And there's essentially no right or wrong in the emotion labeling, because this is how I feel about when I heard that example, for example. But you can use sort of some kind of consensus criteria to see whether you have good labels or not reliable labels. So there's a lot of ambiguity in this space, the data and the interpretation, and this makes sort of building machine learning algorithms to achieve high accuracy really challenging. So now you have annotated emotion data. You can train a machine learning system. I'm just showing you a very typical machine learning system that takes acoustic features only. So you have audio going in, goes through some feature extraction process to turn this into a sequence of, say, spectral vectors representing the information in that audio. And then that sequence is fed through a recurrent neural network, and then that will derive a what we call embedding, which is a high-level summary of the relative information in that audio. And then on top of that, you can add a classifier. In this case, it's just a simple fully connected layer. And then you can use that to predict, say, activation. Actually, this is 4 different emotion categories: anger, happiness, sadness, and neutral. And the beauty of the modern-day neural network-based machine learning approach is that it's almost like it's black magic, right? Or you just feed the data with the input and desired or the expected prediction output to the system, and somehow the system will learn the input and output relationship. You don't have to understand why. It just kind of works that way. But certainly, there's a lot of art or trick or art, depending on how you describe it, to how you can train the system. So one of the challenge for speech emotion recognition is that so much information is packed into that one-dimensional signal, right? The audio waveform. And you have what the speaker said, how they said it, and the speaker's voice characteristics, and even the recording channels. I think we heard this example from this morning's keynote, where in this extreme case, the data were somehow correlated with the scanner that's used for taking those pictures. And then as a result, your prediction of patient outcome is basically based on which scanner the data is coming from, because the machines are just learning the associations. It doesn't know why. It's just that association works the best for getting the highest accuracy. So at this point, I'm going to bring my colleague Viktor on the stage. He's going to talk to you about some of the techniques that can guard against those kind of learning, and also just in general how we address these kind of challenges. Thank you.
Thanks, Chao. So I'll talk about 2 studies, and I'll present our recent research work on emotion recognition from speech. The content is based on 2 papers, one that is recently presented on ICASP this year, and the other which is accepted for publication at ACL 2019 conference. So as you can see from the titles, these 2 studies address different challenges in emotion recognition from speech. This is work done in collaboration with Sri and Gustavo, who were interns at the time the work is done, and scientists in Chao's team, Wang and Ming. I guess the work was fun, since Sri decided to join Amazon in the meantime, and Gustavo is doing his second internship with Amazon. So I will start with a brief overview of both studies, and then in the second part I'll do a somewhat deeper dive on each of them. So first study is on a multimodal speech emotion recognition. So what does it mean multimodal when you have only speech? Yes, the original source of information is a source signal, but it can be processed in different ways, and the way you process it defines modality and associated features. In our work, we are working with the acoustic and lexical modalities and corresponding features. So in particular, acoustic features are descriptors that are capturing spectral, prosodic, and voice quality properties of speech. while the lexical features are based on the word sequences obtained through the automatic speech recognition. So, as Chao mentioned, the acoustic features are describing more or less the style, how you said something, and the lexical features are describing the content. As you've seen in the examples, they are both important for emotion recognition. So after the features are extracted, they are fed into a model. In our case, this will be different neural network architectures, and then we finally make a prediction. In this case, A for anger, H for happiness, S for sadness, and N for neutral emotion state. So this is a bit of a generic representation of the multimodal speech emotion recognition. So what is some sort of novelty in our paper is that we proposed a specific way to fuse acoustic and lexical information at the word level, and then aggregate these fused information that we called acoustic words over the full duration of sentence. And additionally, we explored a learning approach that allows us to train a model that will make emotion inferences on acoustic-only features using both acoustic and lexical features in training. So the second study is focusing on acoustic-only emotion recognition and is based on adversarial autoencoder neural network architecture. So since we are interested in acoustic only, we are feeding acoustic features to the encoder. Encoder is transforming these features to a lower dimensional representation from which decoder reconstructs the original audio features and also predicts the emotional state. In this case, it's valence with the 3 levels, negative, neutral, and positive. And the role of adversarial learning is to regularize the learning process in a specific way and make the representation we learn better. And I will talk about that later more. So what is interesting about this architecture is that although we don't report these results in the ACL in the ICAST publication, it is possible to use this architecture with the partially annotated data. For instance, where you have a large amount of unannotated data and a smaller amount of data with emotion tags. So Dataset is shared across both studies, and that is USC IMOCAP dataset. This dataset contains about 12 hours of speech, and that is 12 hours of dialogues. Each dialogue is a dialogue between 2 actors. There are 5 pairs of actors, total of 10 speakers. And these actors are acting according to, their interactions are scripted but improvised. So they are not reading or anything like that. So after data collection, the data was manually segmented into sentences and annotated at the sentence level. Each sentence, each of 10,000 sentences was annotated by more than 5 annotators, and they annotated it for different emotional targets. So they did it for emotion dimensions, activation, valence, and dominance on the 5-level scale, and they did it for emotion categories for anger, happiness, sadness, fear, disgust, surprise, and neutral. So in this study, we did not use the original annotations as the targets, but our prediction targets were somewhat different. So for instance, for the emotion dimensions, we took all annotations from different annotators and averaged them. And the score that we obtained was quantized into 3 bins, which was low, medium, and high for activation and dominance, and negative, neutral, and positive for valence. On the emotion category side, we picked whichever category got the majority votes from the annotators. Additionally, we discarded some categories. We discarded fear and surprise because they have a very low frequency in the data set that we used, and we discarded disgust in order to match other literature in domain. It's also worth noting that the category happiness was composed of the sentences originally annotated with happiness and excitement. So we have a data set. Okay, in order to start training a model, we need some features. And we talked about multiple modalities. We mentioned acoustic and lexical features. So let's see what they really are. So acoustic features, there are two types of them. One type is the frame level features, and the other type are sentence level features. So frame level features are obtained by extraction of spectral, prosodic, and voice quality descriptors on 25 millisecond snippets of speech. Each snippet is therefore converted to a vector of descriptors. So therefore, you have a sequence of vectors. So effectively, we transform the high sampling rate single-dimensional signal into lower sampling rate vector sequence. And these are low-dimensional features, and they can be used directly for machine learning. Essentially, they capture temporal properties of speech, and the model can learn how to interpret them, and basically will derive from them, learn the temporal patterns that are important for emotion recognition, and derived desirable representations. So on the other side, we might want to temporally aggregate these features. And if we don't want to leave that to a model, we can do it using a hard-coded and somewhat expert knowledge-inspired transformation. So what is done is we look at the per feature time series, which is one-dimensional time series, and then we extract multiple descriptors of that time series. So basically, we apply multiple functions on that time series, and each function gives us one number. And that can be, for instance, mean of values, it can be standard deviation, higher order moments, some global trends, or statistics of rising and falling edges. So therefore, we are obtaining this vector, which is has as many dimensions as the number of functions we apply to this time series, and we concatenate all these vectors for different descriptors. So this is our handcrafted sentence level or full signal level representation. So lexical features are obtained in two steps. The first step involves automatic speech recognition, which gives us a sequence of words. And then we are converting this sequence of words into a sequence of word embedding vectors. So the question is, what are word embedding vectors? So these are vector representations of words that are capturing syntactic and semantic properties of words. There are many flavors of these representations, and they share the fact that they are trained on a large amount of unlabeled text corpora. So in particular, in this study, we used deep contextualized word representation, which is based on a character level language model. So depending on how you do your ASR decoding, that might give you some benefits, in particular recognizing morphological cues for out-of-vocabulary words. So we have described our data set, we described our features, and before we start training models, we want to describe performance metric. In particular, in both studies, we had a classification problem, whether it was a classification of emotion categories or classification of these three bins of emotion dimensions. So therefore, we used a typical measure, which is used in the emotion recognition literature, which is unweighted accuracy. A property of emotion recognition research data set and also real data is that it's highly imbalanced with respect to different classes. For instance, you will see that the neutral class is the most frequent one, and it's not appropriate to use some metric like accuracy, because even some trivial classifier, which will always predict the most frequent class, would get a reasonably good accuracy, but it would be meaningless. So therefore, we are calculating accuracies on all one category versus all remaining category as a binary classification task, and averaging these, so that basically even the least frequent classes get the same impact on the performance metric. So similar for the emotion dimensions. In particular, no matter if you do 3-level quantization, if you stay at the original 5-level quantization, the bin, which is corresponding to the middle, which is neutral for valence or medium for activation and dominance will always be the most frequent one, and therefore we use the same metric. So this is basically what is shared between two studies. So we have dataset, we have features, and evaluation metric. And now let's go into different studies. We will start with multimodal speech emotion recognition. So basically setting when we assume that we have both acoustic and lexical information, both at training and inference time. So I will start by describing, I would say, intuitive and a natural model which can be used as a baseline for multimodal emotion recognition. In particular, that model takes two inputs. It takes acoustic frame level features, and it takes a word sequence which is converted into word vector embeddings. These sequences of frame level features and word vector embeddings are passed through independent recurrent neural networks, and after each frame or each word embedding is fed, one output is produced. The final output after the last frame or after the last word embedding represent acoustic sentence level representation or lexical sentence level representation. These are concatenated to form a joint representation and fed to a classifier. So we mentioned that we are using recurrent neural networks, so I'll just, probably most of you work with that and know it, but I will just mention that these are different from, for instance, fully connected neural networks in a way that they are stateful. Essentially, the output of the recurrent neural network depends on its input and internal state, and every time you feed a new input, you both update internal state and calculate the output that is a function of state and input. While for the, let's say, feed-forward neural network, it's just a function of input. So how do we train this model? Basically, we need fully annotated data, we need acoustic features, we need ASR decodings, and we need emotion labels. And let's see what kind of performance we can get with this model. So here is the performance. There are two bars. The left bar in this Remars turquoise color is corresponding to the acoustic-only model. And that is corresponding to the part of this model that you get when you carve out all red pieces. So you see you get some performance. And then you have a full model, and you get performance for the multimodal. So you can see that the performance significantly improves. And that's expected and intuitive. By fusing two sources of information, you can get a better performance. So the question is, this is reasonable, this is easy, but can we do better? And are there any specific properties of lexical and acoustic information that we did not use so far? And the answer is yes, and there are properties that we haven't used. In particular, acoustic and lexical information are processed independently and just fused very late in this information processing stack that is implemented by a neural network. So we don't have interplay between acoustic and lexical at the smaller time scale. Also, all acoustic inputs are equally important, or lexical inputs are equally important. There is no emphasis on a particular segment in a sentence, and also both modalities are equally important. So we would like to address that using proposed hierarchical architecture. So basically, and address these shortcomings. And what we propose depends on one additional source of information, and that is that ASR is providing us alignment of the coded words with the original acoustic signal. So let's dive into that. And instead of describing what is the mathematics behind it and how actually layers look like, I will go through one example, basically inference example of how this hierarchical architecture processes one particular sentence. So here it is. We are assuming that we have a sentence, oh my gosh, and that we have alignment with the acoustic features. So each word has its own piece of acoustic features. Acoustic features are processed through a recurrent neural network, obtaining the acoustic representation of the word. That representation is augmented by the vector word embedding, and we get a word-level representation. Now we say both modalities are not equally important. Therefore, we have a fusion module, which is essentially implemented as a neural network layer, and that fusion module is taking this feature vector as its inputs and providing the scores of how important is acoustic information compared to the lexical information. Then, having these scores, we are calculating weighted average of these two vectors, and that becomes our first input, our first word input to the second level in the hierarchy. So we do the same for the second word, my, and the same for the third word, gosh. And so now we have a sequence of inputs, first, second, and third. That is again fed into a second level, which is again recurrent neural network. And that network is producing a sequence of outputs. And now we have a new module, which is attention module, and that module is telling us how important each output is with respect to the emotion prediction. So taking all outputs into account, the attention module is producing scores for each output. And again, calculating weighted average of these outputs, which becomes now our representation of the full sentence. So we addressed all these three things that we mentioned up front. Finally, that is fed to a classifier, and the classifier is making predictions. So before we go into analysis of how much this improved our performance, let's go through two examples. Basically, since fusion and attention are implemented as layers in the network, we can inspect activations of these layers, and we can get an insight of what the model thought while it was processing this sentence. So basically,
Oh my god.
oops, sorry, I played it before I thought. I just wanted to describe what is this. So basically, we have importance of acoustic features, importance of lexical features, and basically we have them per word. And we also have a grayscale, which is telling us which word is more important according to the attention module. So for this first example, it was essentially the one that we already went through. It's, oh my gosh, we see that acoustic modality was more important. And that's reasonable, because just if you put it on paper, oh my gosh, it's very emotionally ambiguous. Basically, it depends how you say it. And the word gosh was the most important, probably because it is still a little bit biased towards certain emotions, more biased than words oh and mine, which are pretty generic. So let's go through the second example.
Yeah. We'll call him. We'll figure something out. I'm sorry. You're right.
So here we again can see that if we read the sentence, maybe for this sentence it would be clear, more clear, but the still acoustic information was more important than lexical information. But what is interesting is that although for all the words that were marked as important according to the attention module, we do have that acoustic is more important than lexical. These words actually are very specific and prominent in semantic sense. So it looks that although the model knew that that acoustic features are more important, it also managed to leverage lexical or semantic information in a proper way. So this is, again, all anecdotal, but it's interesting to get some interpretation. So let's go to the results. So what we have here is our acoustic model only, and here we have three versions of a multimodal model. So we have a baseline, which is the first model that we've described. Then we have a hierarchical model, but without modality fusion and attention modules. And finally, we have the full proposed model. So what we can see that multimodal approach improves performance, and that we get benefits even if we don't have the modality fusion and attention. We have some more benefits. So although the differences are not huge, these were at the moment published, the state-of-the-art results on the iMockUp data set, and all differences were statistically significant. So this was all in the situation where you have both acoustic and lexical information at training and inference time. But what about the situation where we want to train with acoustic and lexical and make inferences on acoustic only? And that is addressed by the second part of this study, which is multi-view speech emotion recognition. So let's go into this one. So basically, we are training simultaneously two models. One is acoustic model, which we want to use for inference. The other is more powerful multimodal model. So we train them jointly so that both models predict correctly our prediction targets. And prediction targets have a form of one-hot vectors, in this case, which emotion category got the highest number of votes. But what are additional training goals? So essentially, we want our acoustic embedding to be as similar as possible to our multimodal embedding, enforcing additional transfer of knowledge from the multimodal model to the acoustic model. And this is implemented through a contrastive loss. So basically, the contrastive loss tells you that the acoustic embedding has to be more similar to its corresponding multimodal embedding than to the multimodal embedding of some other random sentence that has a different emotional label. I won't go into details of that, but it is very important how you select that third random sentence that has a different emotional labels. So this is fine. However, it's hard to imagine that this more powerful model can benefit from joint learning. Simply, it already has both sources of information. And this led us to an alternative approach where we had a student-teacher learning setting. In particular, more powerful model was considered to be a teacher. That model was trained in advance, and its weights were frozen afterwards. So the consecutive part of training was not joint. What acoustic model was aiming to learn is to learn similar embedding as the multimodal model, as in the previous case, but it was not learning to predict the original prediction targets, which are one-hot vector embeddings, but instead it was learning to predict the output of the multimodal model. So why? Because let's imagine a sentence where majority vote was happy, and the multimodal model, through learning from multiple examples, learned that it is not a prototypical happiness. It's not only happy, but there is some chance that it might be some other emotion. So this ambiguity is important information for the student, and the student can learn a lot from that. So this is how we did the training, and here are the results. So on the far left side, we have acoustic-only model. On the far right side, we have a multimodal baseline, which is least powerful multimodal model. And in between, we have the Multiview Learning model, where we had the joint training, and the second student-teacher learning. So what we can see that these Multiview Learning models ended effectively midway between the lower bound, which is acoustic-only, and the upper bound, which is multimodal. And that's nice, because you can see that at expense of being willing to apply this a bit more complex learning algorithm, you can train a model using both sources of information, but it will work better than the model that you would be initially trained as your baseline. And at the inference time, it doesn't matter how much you suffered at training. So this is basically concludes the second part of our first study. And now I will move to our second study. And I will present this in a sequence that describes our thought process, basically what we thought while we were coming to our model that we eventually proposed. So let's go. So this is pretty similar to what you've seen already and what Chao showed in one of the first slides. basically, in conventional approach to emotion recognition, we would take the acoustic signal in the form of frame feature vectors or sentence feature vectors, doesn't matter, pass it through some encoder, which would essentially learn preferable representation for recognition of emotions, and finally we will do emotion recognition. So when this is an appropriate choice? This is appropriate choice in the situations when you have a lot of data to effectively train this model using fully labeled data, and if you are not interested in anything except emotion recognition. However, it is hard to imagine that the representation learned here for this particular task would be reusable for something else. And from practical perspective, you might want to make inference with a single model for multiple tasks instead of creating a separate model for each task. So additionally, we know that emotion annotation is costly, and that we will always have much more data that is unannotated than the data that is annotated with emotion labels. So the question is, what kind of representation can help us to solve these problems? So basically, we can maybe train it with the partially annotated data, and it might be reusable for different tasks. And definitely, it's a representation that allows you to reconstruct the original signal. So therefore, we get to the autoencoder architecture. Basically, we still have the same encoder that is providing us some latent representation. And from that latent representation, we are able to solve two tasks: to reconstruct the original acoustic representation and to predict emotion. And this is nice because such a model can be trained with partially annotated data. You can imagine that this part of a model, everything except this classifier, can be trained in an unsupervised fashion, just predicting the input. And then for the remaining part of data, you can basically use both losses, reconstruction and classification loss. And this is great, but there is still a question, can we do a bit better? And here is the answer. Yes, probably yes. We can use adversarial autoencoder. So what is the difference between adversarial autoencoder and autoencoder that I've presented in the previous slide? Essentially, the difference is that adversarial autoencoder uses adversarial learning to regularize the learning process and make this latent representation fit particular prior distribution. So how it's done? Basically, if we have a set of samples and we pass them through the encoder, we will get the latent representations for these samples. And let's assume that we give them label 1, which means created by encoder. On the other side, we will create the same number of samples using the sampling from that prior distribution, and we will give them label 1, which means created by random distribution. And then we will ask this guy, which is discriminator, to predict correctly whether the sample comes through this path or through that path. So this type of adversarial learning is trained in phases. Basically, if we have a fixed generator, then we'll train discriminators to maximize this classification performance. And after that, we will fix the discriminator and retrain the generator to make the task for discriminator more difficult. And we will cycle these. So that's it. So we can see that here we have some kind of monolithic latent representation that is used for reconstruction, for emotion recognition. Maybe it can be used for something else as well. However, here is how we'll look at the speech generation process, and Chao mentioned it already. We think that a speech is generated from multiple latent factors, and definitely content is there. We have age of the speaker, gender, speaker style or speaker traits, and emotional state is there. And what we want to do is we want to take a speech signal and we want to make inferences on these latent variables. However, in our previous model, the latent variable representation was monolithic. And now we want to basically say that latent representation is partially only emotion, like part is dedicated to emotion and the part that is capturing everything else, all these other latent factors that we have. And that is how we get to the model that we actually proposed in this study. And that is this model. So if you can see that we split our latent representation into two parts, one part that is for emotion representation and the other capturing all other latent factors. Now, since we still want to use adversarial learning, we have two discriminators. One discriminator that is applied for this part of representation and the other applied to the different part. So this is kind of continuous. So we want to fit it to match the zero mean unit covariance Gaussian of this dimension. And for this one, we wanted to match particular categorical distribution that is essentially prior to distribution of different emotional classes. So, so how did we? So it's worth mentioning, and we did all these experiments, that this model can, this learning approach can be applied to different model architectures. So far, we haven't mentioned what is here, what is here. So what is your encoder and what is your decoder? And we applied it both for frame-level acoustic inputs and sentence-level acoustic inputs. For frame-level acoustic inputs, we used convolutional neural network architecture, where encoder was combination of convolutions and pooling layers, while the decoder was implementing inverse transformation of transposed convolutions and upsampling. For the acoustic, for the sentence level acoustic representations, these were fully connected layers both for the encoder and decoder. How do we do training in this case? Basically, we do training in phases. In the first phase, we only train encoder and decoder to do reconstruction. In the second phase, we are training, we are applying this adversarial learning with both discriminators, so there is no reconstruction loss. In the third phase, we are only training this part of model to predict emotional classes. So basically, we are enforcing this part of latent representation to be a correct prediction of emotional class. And since this is a reasonably complex learning approach, there are a few tricks that were necessary. And we don't have a time to go why and how exactly, but I will just mention that it was important to use batch normalization in different layers, dropout in discriminators, and to properly adjust learning rates of generator and discriminator. So finally, we get to the results for this model. So we have two groups of 4 bars here. The left group is corresponding to sentence level representation. So basically, when your acoustic input was sentence level acoustic input, while the right group is corresponding to the frame level acoustic representations. So let's look into one of them because they are comparable. And what we claimed as a success is that on such a small data set, we managed to train a much more complex convolutional model with the same success as a fully connected model, which is usually hard for the small data sets. When we have, if you had more data, this is supposed to go up, while this might stay slightly higher or at the same level. So this one was the baseline for the sentence level, which is just the first model I presented, which is just the inputs, encoder, and classifier. Then the far right is proposed model. And in between, we have 2 versions. The first one is just adding additional reconstruction loss, basically autoencoder, no adversarial learning. And the third one is the one that is applying adversarial learning, but treats the latent space as one monolithic latent space. So there is no split between emotional and other part. So all these differences are small, but statistically significant. And again, the big advantage of this model is you can repeat these experiments on partially annotated data where you expect to get a full benefit of this type of architecture. Additionally, we looked into how the model performed on different speakers, and we've seen that for 8 out of 10 speakers, the model proposed model performed better than the baseline 2 to 6%, and only for 2 speakers, performance dropped less than 1%. So with that, I would conclude a presentation of these 2 studies, and I get back to Chao for potentially if you have some questions. Thank you.